This presentation will describe what I refer to as quantum strands and loops. A quantum strand is a path defined as a sequence of angular bends and rotational twists. Specific angle values can be assigned to the bends and twists and provide a quantum description of a strand. Some strand sequence definitions result in forming a closed loop. The example here shows the yellow arcs representing the dihedral angle of a tetrahedron, and the green arcs represent the dihedral angle of a cube, and the white spheres represent where the twists are made in each of the strands. A quantum strand will be illustrated as a sequential connection of arcs. Each arc in this sequence is defined with a particular bend angle. A subsequence of letters, A through J, is used to define the bend angle for each individual arc in the strand, where each letter is assigned a unique angular value seen below. This bend subsequence can contain one or more letters and is repeated until the desired length of the strand is reached. The dihedral angle of each of the platonic solids are assigned to 5 of these letters, and for each dihedral angle there is a corresponding conjugate angle where the sum of the dihedral and conjugate angles is equal to 360 degrees. This is a tetrahedral arc pair that uses the dihedral angle of a tetrahedron and its conjugate angle, and the sum of bend angles A plus B is equal to 360 degrees. This is a octahedral arc pair that uses the dihedral angle of an octahedron and its conjugate angle, and the sum of bend angles C plus D is equal to 360 degrees. This is a cubic arc pair that uses the dihedral angle of a cube and its conjugate angle, and the sum of bend angles E plus F is equal to 360 degrees. This is the icosahedral arc pair that uses the dihedral angle of an icosahedron and its conjugate angle, and the sum of bend angles G plus H is equal to 360 degrees. This is the dodecahedral arc pair that uses the dihedral angle of a dodecahedron and its conjugate angle, and the sum of bend angles I plus J is equal to 360 degrees. Quantum strand twisting. Each of the connections between the arcs of a strand are defined with a twist angle. The twist angle between two arcs is measured as the angle between the planes that contain each arc. The twist angle is 0 degrees when both arcs exist on the same plane. Non-zero twist angles have a step or magnitude with a direction that can be clockwise or counterclockwise. Quantum strand twist sequence nomenclature. The twist subsequence is represented by a sequence of digits 0 through 9, where each digit can be assigned a particular angle value. This twist subsequence can contain one or more digits and is repeated until the desired length of the strand is reached. The twist angles are grouped according to the vertex of the platonic solid that the arc bends are based on. This is determined by the number of edges that form the vertex of the platonic solid. Vertex of 3 can be seen here, where 3 edges converge, and the step between them is 120 degrees. A vertex of 4 is where 4 edges converge, and their step is 90 degrees between them. And a vertex of 5 is where 5 edges converge, and the step between them is 72 degrees. Quantum strand twist inversion. After some experimentation, I found that additional quantum loops can be defined by applying a 180-degree phase shift to the twist angles used between arcs. This results in the following transformation of twist angles. Quantum strand number. There are 3 main parameters to define a unique strand number. The length of the strand is the number of arc elements. The bend subsequence is used to define the size of each arc, and this subsequence is repeated throughout the length of the strand. The twist subsequence is used to define the twist angle between arcs, and this subsequence is also repeated throughout the length of the strand. So combining these 3 parameters, a unique number describes the quantum strand. Most quantum strands do not form a loop. Only a small percentage of quantum loops result in loop structures. Elaborated strand sequence. This is an example of quantum strand being described as an elaborated sequence of bends and twists. The bend subsequence in this example is AB. The twist sequence is 2012 with a length of 12. That gives you the following strand number. This can be elaborated into a series of characters, where the red characters represent the bends and the black characters represent the twists, and can be elaborated fully as seen in this example here. Quantum loops. Some strands result in forming closed loop circuits where the first and last arc of the strand perfectly align. These closed loop circuits are referred to as quantum loops and exhibit harmonic structural behavior with perfectly overlapping patterns of various frequencies. The arcs in the quantum strands can intersect and overlap with each other. This video clip shows some examples of quantum strands that form quantum loops. In each of these examples, the bend sequence consists of a single arc size, represented by a single letter, and the twist subsequence consists of various twist angle values that can be seen in the strand number in the top right corner here. And I'll just let this video complete out to see a few more examples. Tetrahedral arc pair AB, which has a twist angle group using digits 0, 1, and 2. The resulting structure is a tetrahedron which has a vertex of 3 and a twist angle step of 120 degrees. Tetrahedral arc pair structure. A bend subsequence can be defined as a tetrahedral pair of arcs, in this case AB, which is dihedral angle and the conjugate angle of the tetrahedron. In such cases, for any twist subsequence, the arcs are always constrained to the tetrahedral structure seen here. This is the octahedral arc pair CD, again with a twist angle group using digits 0, 1, and 2. The resulting structure is a cube, which has a vertex of 3 and a twist angle step of 120 degrees. Octahedral arc pair structure. A bend subsequence can be defined as an octahedral pair of arcs, CD in the example, which is the dihedral and conjugate angles of the octahedron. In such cases, for any twist subsequence, the arcs are always constrained to the cubic structure seen here. This is the cubic arc pair EF as a twist angle group using digits 0, 3, 4, and 5. The resulting structure is an octahedron which has a vertex of 4 and a twist angle step of 90 degrees. Cubic arc pair structure. The bend subsequence can be defined as a cubic pair of arcs, EF in this example, which is the dihedral angle of a cube and its conjugate angle. In such cases, for any twist subsequence, the arcs are always constrained to the octahedral structure seen here. This is the icosahedral arc pair GH, and the twist angle group uses digits 0, 1, and 2. The resulting structure is a dodecahedron, which has a vertex of 3 and a twist angle step of 120 degrees. Icosahedral arc pair structure. A bend subsequence can be defined as an icosahedral pair of arcs, GH, which is the dihedral angle of the icosahedron and its conjugate angle. In such cases, for any twist subsequence, the arcs are always constrained to the dodecahedral structure seen here. This is the dodecahedral arc pair IJ. The twist angle group uses digits 0, 6, 7, 8, and 9. The resulting structure is a icosahedron, which has a vertex of 5 and a twist angle step of 72 degrees. Dodecahedral arc pair structure. A bend subsequence can be defined as a dodecahedral pair of arcs, IF, which is the dihedral angle of the dodecahedron and its conjugate angle. In such cases, for any twist subsequence, the arcs are always constrained to the icosahedral structure seen here. Platonic quantum loops. This is a comparison of the 5 Platonic quantum loops that resulted from the arc pairing that was just illustrated for AB, CD, EF, GH, and IJ. Complex quantum loops. The bend subsequence could also be a more complex arrangement of different arc sizes, as seen in this video clip. There are examples of bend subsequences that have a length greater than 2, but the arcs are within the same Platonic group. There are other bend subsequence examples that use arcs from multiple Platonic groups. Quantum torsion loops. These quantum strands are constructed in a physics simulator, and the twist connections between arcs can be simulated with torsion-like behavior. This video clip shows a quantum strand being forced into a quantum loop. This injects a torsion force into the structure as the first and last arcs of the strand are connected to each other. This illustrates how efficiently the structure propagates torsion force within the quantum loop as the energy is transferred from arc to arc. A subsequent presentation will describe how to access this quantum loop simulator online.